record. I love it when I remember to record the problems. So on this day 3 of exponential growth and decay, we've done a few things. We've done our graphing. We've identified the characteristics of the equations or of the graphs. So we are going to look here at modeling our growth and decay, how we can use this in real life. That's what we mean by modeling. So the first thing we have to talk about with growth and decay is the equation. So the exponential model looks like this. A equals P, and then parentheses 1. It says plus or minus R to the t value. The plus or minus only means that it's for, you could either add or you could subtract. You aren't going to do both. So if you want, you could even kind of write this out. Your growth problem would be a plus because we're increasing, whereas your decay or your decreasing problems would be the subtraction. So if you want to write them out separately, that might not be a bad idea. We have some variables here. P stands for your initial amount. Its actual word would be called the principal. Okay, I kind of think like bank accounts. Your principal is what you deposit, and then you get your interest rate from there. So R being our rate, we write this in decimal form. So for example, if I said 3.5% interest rate, that's the same thing as 0.35, decimal point 0.35. Okay, if you're not sure, moving your decimal points, remember percents are out of 100, so you could just divide by 100 to get your decimal point. So there's another way to do it. And T, of course, is time. Typically, we're saying time in years, although sometimes, depending on how the equation might be written, sometimes we'll give you the equation and we'll say, oh, it's actually not in years this time, it's in months or in days. But that's in a situation where we're going to give you the equation, not make you write your own. So, all right. So let's take a look. It says on our first equation, first example, a new car costs $23,000. The value decreases by 15% each year. And it says write an exponential decay model for the car's value. So the model, the generic model, it's decay. So we're already telling you to do a decay problem. They also told us that the value is decreasing. So that's our other hint that this is a decay model. So the generic model looks like this. A equals P, 1 minus R to the T. What we want to do is we want to actually plug in the numbers. So we need to know what is the principal, what is the rate, and if we have it, what is the time. In this case, we're just going to write the model. We're not actually going to solve anything, so we're not going to have all of the numbers plugged in for. So our principal is our 23,000, and our 15%, that would be our rate, but it's not quite in decimal form yet. If we write 1 minus 15, that's a negative number. We can't have a base of a negative. So we have to actually put it into decimal form. So really, this is just saying 23,000, 1 minus, I need to change 15% to a decimal. So what's 15% as a decimal going to be?
0.15.
0.15. Beautiful. Okay. Oops. There we go. And there's our answer. There's our model. That's all I want. You can go ahead and subtract if you want, and you'll see this a lot of times. You could write it like this. So all I did is I just did the actual subtraction, the 1 minus 0.15. If you don't, it's fine. It's still going to give you the right, like it means the same thing. It's just you might want to evaluate, make the decimal, the parentheses smaller. You're more than welcome to do that, but you don't have to. If you just plug it in like this with the 1 minus 0.15, that's totally perfect, but it means the same thing if we do the 0.85. Okay, they're the same equation. So now it says use the model to estimate the value after 3 years. Well, that means 3 is our time. So we're just going to plug in 3 for t and type it in our calculator. So I have my 23,000. I'm going to use my 0.85 just because it means I have less to type in my calculator. And then we're going to raise it to the third power. Okay, so I'm going to have, oops, I'm going to move that out of the way a little bit. There we go. So I have my 23,000 times my 0.85. And I want to make sure that I hit the raised to button so that I get the exponent. So raised to the third power. I see a lot of people that write times 3 instead of raised to the third. It's very different. 10 times 3 is only 30. 10 to the third power is 1,000. They're very different numbers. So make sure that you are using the right property as you do this. So because our car is decreasing in value, we now have a car value. Obviously, we don't have, when you think about money, money doesn't have 3 decimal places. Money goes to 2 decimal places, dollars and cents. So we have our 14,124.80. We'll call that 88 because we'll round up. So 14,124.88. That's the value of the car after just 3 years decreasing in value. It says to go ahead and graph the model. I'm just going to bring up my Desmos website. I have a lot of websites open, can you tell? Let's see here. Well, that's interesting that the picture-in-picture wasn't up there. Let's see here. Desmos. I'm going to change my graph just a little bit really quick here so that it's easy to see. Okay, so it says graph the model in the calculator. So we had, I'm going to write A equals 23,123 times 0.85 raised to the t. And clearly we don't see anything because all of the numbers we have here are from -10 to +10 or -6 to +6. So I'm going to have to scroll out quite a bit because I need, oh, there it is. So there's our model. We can see this. If we zoom out really, really far, it basically looks just like a right angle. So it says, right, so we get this kind of model that looks something like this. Actually, it looks kind of suspiciously like that. And it says predict when the value will be half of the original value. So half of the original. If it was originally $23,000, half of that, we need to know what's half of 23,000. So 23 divided by 2.
11,500.
Beautiful. So what we're really going to look at, we could do this a couple of ways. This one. We could look for when we see 11,500. So I could scroll up here, find my 11,500. It's kind of handy here. Where is it? Somewhere in here. We could look at right in here. Easiest way to do this, and I'll write this down, these directions down. I could just say when A equals 11,500. Actually, I guess I'll have to write Y equals because there we go, because it wasn't doing it. So I get this number here. You can see where that crosses the graph that we have. You can see our Y value is 11,500, so about 4.265, just a little over 4 years. And if I zoomed in really, really close, you're going to see this. Here's our 11,500. And here's my 4. So we're right after. So you could zoom in. You don't have to type this part in. Like if I close it out, I still see my 11,500. And here's my 4 on my graph. So I can still kind of see approximately, there we go. There's my 11,500 showing up on the point value. And I can see the 4.265 for my Y value, or for my X value. So that's my years. It looks like for the most part, it doesn't really change much, does it? That's because it only rounds so many decimal places. So what we can do, I'm going to write this down. So you can graph y equals 11,500 and find where they cross. Okay. So our prediction then, it would be about 4.265 years after purchase. Or about 4. If you have a graphing calculator and you're trying to do this at like on one of these, you're probably going to have to change a bunch of stuff on the window to be able to zoom out and move things around. I can show you on this graphing calculator too, just so you can see it. So if I was going to graph the equation, I'd have my 23,000 times my 0.85, or 1 minus 0.15 raised to the x, okay, because it doesn't do a and p, it does x and y in these calculators. And then I would type in my second equation as well, would be my 11,500. Oops, too many zeros. There we go. If we want to see it, we would have to change our window. Our x's don't really matter, it's the y value. We could go start at 0 and go all the way up to, I don't know, 24,000. Obviously, not counting by ones. What would I count by? So the y scale, that's what I'm counting by. Let's count by, oops, 1,000. There we go, graph. So now we can see that, and by changing that scale, it also made it graph it faster. But now I can kind of see the idea of where we're at. It looks like we're crossing, yep, right about just after the 4. So I can see that. So I've had to change the window. So that's how I did that. I went to the window to change what scale my graph is going to be on. So that's another way to do it. If you want to know where they cross, you could either trace, just hit the trace button here, and you could sort of, oops, do. So we could see this. Or, so there we go, 4.24 is kind of where it looks like it's pretty close. You could hit second, trace, and you could find where number 5 there, where they intersect. And you just hit enter, boom, boom, boom. And there it is, 4.265, which is what we said we were going to have on our, oops, on our problem. So lots of different ways to do it. Desmos is probably more user-friendly, but if you have your own calculator, it's not a bad idea to know how to use this when it comes to the SAT and you are trying to do these kinds of problems on the SAT, because they won't let you use Desmos on the SAT. So, okay. Alrighty. So that was our first question. We're going to do one more just like that. Just kind of get some practice with it. And we have one more formula that we're going to do here, which is really just more plug and play. We're just plugging the numbers in to get them all figured out. Okay, so in 2005, about 2,180,000 US workers worked at home. I think that's a lot more right now. During the next 10 years, the number of workers working at home increased by about 5% per year. And then 2020 hit. Write a model giving the number W in millions of workers working at home T years after 2005. Okay, so one of the big things, or one of the things that's a little different about this problem, is that now it doesn't say just write a model with the number working at home. It says write the model in millions. So this means that our 2,180,000, they want us to kind of shorten that information. They want us to kind of shrink it down a little bit so that there's not as many zeros. So when we say 2,180,000, that's the same thing as saying 2.18 million. You guys have probably seen that before, right? Another way to write or read the same kind of information. So it says take all those zeros off. I just want to know we're talking about the 2 million, so we want to put that in kind of into its shortened form. We need to know our rate. Looks like our rate is about 5%. So we're going to change that to our decimals. So we're going to say our amount, or actually they're going to say W. They want us to use W instead of A. Our workers is going to equal about our initial amount, 2.18, times it's increasing. So we're going to add to our 1 plus our 5%. Now again, I'm not going to write 1 plus 5. I need to change 5% into a decimal. So 5% would be 0.05. Okay. 5% is 0.05. And then I would just raise it to the t value. So there's my equation. That's all that first part is. The equation is the easiest part in here. It then says use the model to estimate the value after 5 years. So that means this is now our time. And so we'll plug in 5 to the equation. So we'll do 2.18, 1 plus 0.05, or you could just write it as 1.05 raised to the 5th power. You'll find that a lot of times I do condense these just because it's less writing. I don't have to do as many symbols. It doesn't take as long to write it that way. So now that I have the value, let's plug it in. 2.18 times 1.05 raised to the 5th power. So I have about 2.78. We'll go with that. 2 decimal places is probably fine. Remember, this is talking about in millions, so about 2.78 million workers working at home. Okay, so it's increased by about 60 million people in 5 years. I'm sorry, 60, well, it'd be 600,000. There we go. Now this time, graphing the model is actually a little bit easier. Because we've shortened the numbers, we don't have to change the scale as much. So if I was to go to my Desmos, it means, let's see if I can, just trying to think if there's a way for me to reset my graph. And zoom it all the way out. I gotta scroll all the way. That's one thing about Desmos. I don't think there's a reset button. Right? No, that's share. I don't need to do that. And that's just, oh, wait. Oh, there is a reset button. The little home button, will take you back to your 1010. Oh, that's very handy. I didn't know it did that. The more you know. Anyways. Okay, so we said our equation was, our model was W equals 2.18 times 1. You could write plus, and I'll show you that. 1 plus 0.05. And then you want to raise it to, so exponent to the t value. Doesn't really look like much. And I'm just going to show you guys, this is the same thing. W equals 2.18, 1.05 raised to the t value. It's the same graph. You see how there's no difference in the equation in the picture? So just so you know, doesn't matter. So there's our graph. It kind of looks like a flat line. Kind of looks like this. Whoop. We don't see the curve on it as much because it's zoomed in so closely. If I was to zoom this back out, now you can start seeing its exponential growth as you look at it. So look, home button, boom, back to the regular Zoom. That's so handy.
Miss Kane, you have to think of it as home makes you whole, and a 0 is whole.
There
is a whole.
It is?
It looks like one.
Yeah. Oh, I like it. Okay, I have to know. Did you guys know that that button did that, or was it, or no?
No.
Okay. All right. At least I don't. I'm like, did everybody else know that that button worked, and it was just me not knowing it? Like, that's very, very possible. Okay, so
Lainey
it says.
said she did that.
Oh, oh, I didn't see the. I closed my. Oh, jeez, Lainey, you got to share your information. It's okay.
Sorry, I'm the only one who's talking here anyway.
Yeah. So it says use it to estimate when it's about 3.22 million workers who worked at home. So right now we've seen it. We knew it took 5 years to get to about 2.78 million. We want to know how many years. So it's going to be more than 5 to get to 3.22 million workers. So here I could either kind of look at it and go, all right, well, there's 384. I could kind of drag and drop, till I'm about 3.2 or 3.22. Oh, there we go. So it looks like about 8, or you could do and actually type in, I'll just type y equals 3.22. And now it actually intersects, and I can see very clearly, it actually says 7.995, which is close enough still to 8 to call it 8. So approximately 8 years later, but it doesn't say how many years, it says the year. Okay, so we want to know which year it is that they have about 3.22 million workers. So this problem started in 05, or these people working from home, our model starts from 2005. So about 8 years after that,
2013.
There you go. So we're just adding. So really it's just saying 2005 plus 8, we're saying the year would be 2013, that about 3.22 million workers worked at home. Okay, so this one, it does take it a little bit. It's not saying just the number you see on the graph, but what do you do with the number? So it's kind of paying attention to those little pieces of information. Okay. So hopefully, for the most part, those models, they're not terrible. You're going to get some information and you just plug it into the equation. We've got one more. It's basically the same thing. Oh, so kind of think about, how are we feeling on this? Easy peasy. Hopefully it's easy peasy. Might be on the fence. I hope I don't have anybody that's totally lost. We're going to do a little bit of practice here in just a minute too. I have something fun. So rather than doing the my turn, your turn on the back, I have a my turn, your turn for us on a pear deck. I'm so excited. It's fine. All right, so we have one more formula. This one's a little bigger, as you can see. It still has the same basic ideas to it, but there's a little bit more. So it's still the A equals P times 1 plus R raised to the T, but now we're throwing in one more letter in here. And it's the same letter. It's saying that now when we're doing the interest or when we're dealing with it, and this is something you see a lot more with bank accounts and finance, where we're saying it's going to be compounded, meaning you're going to get interest more than one time per year. And so a lot of savings accounts, they do interest quarterly. So if you have a savings account, every once in a while, like every 4 months, you're going to see approximately, like a couple of cents or something added to your account. That's when they're compounding their interest. So they're saying, all right, well, maybe I give you like 3% interest, not, but 3% interest. So what they do is they say, all right, 4 times a year, I'm going to give you that interest, but I'm not going to give you 3%. I'm going to divide that 3% by 4, but then compound it 4 times. So it's kind of a strange, like crazy way that they do some finance. So that it's not like you're going to get one lump sum. Go ahead.
In December, I got like 6 cents out of my account for my interest rate.
Woohoo! Paula.
There's not much in there, but
I've
I
been
only
there.
have it's a lot, but I tempt myself not to transfer it to my checking account, so.
Mm-hmm. Oh, it's so hard. It's like, oh, I could really use a new pair of shoes, or I really kind of like that outfit. But you gotta, try to keep yourself from
Well,
spending it on things you don't need. That's hard.
yeah, that's the thing, because I work at Old Navy's and I get 50% off discount, so I tempt myself a lot buying clothes
I'm
from
gonna
there.
give you my shopping list, and you could just pick some stuff up for me. It's fine.
Okay. We're not supposed to do that,
I know.
but as long as they don't find out.
Yeah, as long as they don't find out, it'll be fine. No, I'm totally joking. But oh my gosh, I would really struggle working at Old Navy. That's where half my clothes comes from. Okay, so here's our formula. Looks like this. It's very, very close to the formula we just worked with. The only difference is that we now have this n that's added in that it didn't have before. So if it's just compounded one time per year, that n becomes a 1, and then it's the exact same formula we just did. So the difference is sometimes it's compounded. So annually, so there's a couple of words here that we're going to identify. So when we say something's compounded annually, we mean once. If it's compounded semi-annually, then that happens twice per year. Okay. If it's compounded quarterly, that's when we see, just like a quarter, there are 4 quarters in a dollar. Quarterly means it's going to happen 4 times per year. And that's typically what a bank account is, quarterly or 4 times during the year. If it's compounded monthly, then we have 12 months in the year. This one's kind of tricky, bi-monthly. So it kind of depends on the situation. Most of the time when we say bi-monthly, we're talking about every 2 months. So bi-monthly is kind of breaks the cycle of what we had here where everything's increasing. Bi-monthly meaning every 2 months. So it would be 6 times per year. Oops, I wrote 2 again. Nope, that's not it. 6 times per year. I can do this. Spelling, not always my strong point. There we go. Bi-weekly, or like sometimes people go, oh, bi-monthly, that means like every half month, but that would be more like a bi-weekly situation. So bi-monthly, every 2 months. Bi-weekly would be every 2 weeks. So we try to use that to help us kind of work that out. And then daily, how many days in the year? That's an easy one. I guess that would be our
365 days.
You got it. 365. So, and like if we had said weekly, there are 52 weeks in a year. We didn't want to overwhelm you with all of the different possibilities. These are the ones that come up the most often, especially that quarterly, monthly. Actually, really, quarterly and monthly are the ones that would come up more often than others. So just to kind of show you guys how these look and how they can change the interest value. So here's our equation. We're not going to do anything too crazy with these. We're going to have you guys just plug some numbers in and calculate it. So I'm going to bring that equation along. Actually, can I just grab it? I can. All right. Copy. So this is on the back of the notes. We're just going to do these 3 at the top, and then instead of the my turn, your turn here, I'm going to have you guys join a little pair deck, and I'll give you a quick little break, like a mental math break, and then we'll do a little pair deck for some fun interaction. Imagine that. Okay, so I just brought the formula along so that we could see it a little better because it's hard. It's a big formula and there's a lot to remember. So it says here, you deposit $1,500 into an account that pays 6% annual interest. Don't know where that account is, but I'd really like to join it. Because most banks right now are about 1% to like 0.8%. So we're talking almost no interest. The interest rate right now is really, really, really low. It's great for loans, student loans, mortgage payments, that kind of stuff, but it's not great for your savings account or trying to grow any kind of money. So it's good in one way, but bad in another. So you deposit $1,500, it pays 6% annual interest. Find the balance after 2 years if the interest rate is compounded. So we're going to do this 3 different times and look and see how does the compounding change what your final amount is. So we're going to start with annually. So that means our N is 1. So 1 time per year. So that's basically the same function we had been doing before. So let's go ahead. I'm going to plug these numbers in. 1,500 would be P. 6%, there's our R, but remember we're going to make it as 0.06. We got to change that decimal point. And then 2 years, they're already telling us there's our T. So this is just a matter of typing it into the calculator for the most part. A equals, we're going to say 1,500, 1 plus R, our R is 0.06. Our N, we said it's annually, so that's 1 time per year. So really nothing changes here. 0.06 divided by 1 is still 0.06. And then raised to the N times T. T is our 2. So just plugging it into that formula right there. You could work this out a little bit if you want, or you could type the whole thing in your calculator all in one go. I'm just going to kind of condense this a little bit. No, I'm not. The one thing I would recommend maybe is kind of calculating out your exponent if you need to. 1 times 2, I just get 2. So I have 1,500, 1 plus 0.06 divided by 1 raised to 1 times 2. I'm just going to put raised to the second power. Okay, you could write 1 times 2 if you want, but you don't have to. So I get 1,685.4. So $1,685.40 would be our answer here. 1,685.4. Okay, so in 2 years, using a 6% interest rate, compounded annually, you've basically gained $185.40 in 2 years. That's a lot of interest when you think about like what Alexa said, that she had 6 cents put in her account. Yeah, that's you don't get this kind of interest rate. I'm just going to go ahead and tell you guys that. Sorry to burst your bubble. So now let's look and see, well, what happens to the interest, or what happens to the amount that we get at the end if we change the compounding period? If we say it's now semi-annually instead of annually. So twice per year instead of once per year. So it's the exact same numbers. We're still starting with a principal balance of 1,500. We still have our interest rate of 6%, but now instead of dividing by 1, we're going to divide by 2. Okay, and then we raise to the 2 times 2 years. So when we go to type this in the calculator, same thing, 1,500, 1 plus 0.06 divided by 2 now, because we're compounding twice per year, raised to the exponent would be twice per year for 2 years. So that's 4 times in 2 years that we would have our interest. So now it's not much of a change, but now we're going 1,688.26. So by compounding twice per year instead of once per year, what was that number? 26. We've gotten a little bit more money out of the bank. So we got an extra $3. Not much, but a little bit. That's more like $3 in 2 years is probably more like what you're going to get on an interest, what they'll pay you. They don't want to give you money. It's all a lie. It's all a lie. All right, so then the last one. Go ahead.
With these ones, I just got done doing all like the finance stuff in finite.
Oh.
So I already have these done.
Perfect. Yeah, these ones, yeah, so this will be pretty easy. And this is something that we've done. You guys actually did these exact same problems in Algebra 1 as well. So this is all review, but it's been a long time. So yeah, and if you're in finite or QR or whatever they call it now, then yes,
Yeah.
you've done this whole unit already, so this is super easy.
Oh yeah.
So yeah, now we have our quarterly. So we're saying our n is now 4, and so we're just going to type this in, same thing. Is there a big change from semi-annually to quarterly? Let's find out. 1500, 1 plus 0.06. Now we're dividing it 4 times per year, but that means that 4 times per year for 2 years, you're actually going to raise it to the power of 8. 8 times will you receive interest. And now we get 1689.74, we'll call it. Okay, so a little bit more yet as you start dividing up and calculating all of that interest over and over. Each time you divide your interest by more times, your interest, your value will go up a little bit, to the point where we're actually going to talk on Friday. We'll talk about compounding continuously, which is typically how they deal with loans and things, because they want more money from you more often. So they tend to compound a loan continuously, where they only compound your bank account quarterly. So they want to take your money, but they don't want to give you money. Oh, how rude. So yeah. So if you want to go ahead and do your my turn, your turn, you can. I'm going to give you guys a couple of minutes here. We'll say like 4 minutes. Just take a quick stretch break, because I don't know how much often you guys get breaks in your other classes. I'm going to stop my recording. I do want us to come back, and we're going to do just a couple of quick little like multiple choice. I've got a little pear deck for you guys to interact with to see how you're doing, because tomorrow we have a quiz over our graphing, our identifying our features, and we are going to have a couple of word problems on the quiz as well. So I want to see how you're doing with that. So take a couple of minutes. I'll post. So it's 9:03 now. We'll say like 9:06. And I'll put up the information for Pear Deck and stop the recording and get that all kind of squared away. Take a minute, stretch, walk around for a second, and then come back.